introduced some of the major tasks of high level synthesis in the previous lecture. One important thing to note is that for the same specification in the form of an HDL, there may be a very large number of implementations. Where will all the different variations come from? So, they are not all equivalent. So, somehow the job for high level synthesis should be that we pick up at the end the best out of all the choices that exist. But where are the choices? In this example that we started off with, we constructed an FSM and a data path. This is the output of the behavioral synthesis, but where did we have a choice? Or was this the only possible output from the synthesis process?
So, the constraints we had that we had to use.
Constraints were externally imposed to the synthesis. What are the inputs? We said that the primary input of course is the behavioral description in the SDL, but there are other inputs. The constraints in the form of resources or delay, those are inputs. We do not have a choice. It is assumed that the designer through other means, maybe through whatever external means, there are these constraints that are imposed. So, we have to operate within the constraints. Constraints have to be respected, but within those constraints we may still have a large number of choices. Did we have any choice in this small example that we built up? Where was the choice that was exercised? In the FSM, did we have a choice?
Yes.
What was the choice?
We can insert dummy states.
Could you have inserted dummy states? What in the behavioral synthesis process influences the creation of the FSM? They should make sense. They should arise naturally in some way. What choice did we have?
We optimized everything so that we can finish things in 3 cycles. We can.
Right.
Designer has given the maximum usage of adders, but we can choose.
Yes, the latency, which is 3 cycles in this case, was not a constraint. There are some constraints that it is not clear what they were perhaps, but I did say that in that library when we started off, right, these were constraints, that you have one adder of each type and 2 memories, 1 multiplier and so on. Those were the only constraints, but on delay there was no constraint. So, the schedule that we were working with, which is this one that finished in 3 clock cycles, that was our decision. This is not the only valid schedule. Why did we choose this schedule?
Earliest.
We assumed that constraint that you have 1 pink adder and 1 orange adder in this. So, with that as the resource constraint, it seems as though you perhaps do not have too many choices here. So, 2 additions have been mapped to 1 adder, and that is those 2, and the other 2 additions have been mapped to this adder. This is the function unit binding step, right. That is the function unit binding that has been done for this graph. Did we have a choice? What other binding could have been done?
You could swap orange and pink.
Yeah, you could have done this kind of a sharing, right, maybe this kind of a sharing that would also have respected the resource constraint and also the resulting schedule that we already decided makes sense in the first step. What difference would that have made to the data path? Different hardware. So, what different hardware would have been generated? We are still operating under the same resource constraint, which means that these function units of course would have still been there, but the muxes and the connectivity might have been slightly different. In this example, it is not clear that it makes a qualitative difference to the result, but in general you actually have a very large number of choices. You have a very large number of operations and some number of resources, but the moment the number of resources is more than 1, you have the resource sharing decisions to be made. We also made register sharing decisions here. We said that we will take 2 registers. It seems as though this makes sense for that particular design, but when you have n variables and r registers, well, actually here register is not a constraint. How many registers you use is inferred by our algorithms. So, we did not take that as a constraint, although you could formulate the synthesis problem also in a way that the registers is a constraint. So, here we just wanted to minimize the number of registers that we are using, and a certain sharing of variables into registers was used to generate this part of the circuit, right, the number of registers and also the select circuits at the input of the registers. So, it seems as though in this small example there were not too many choices. Some choices were there, but a large number of choices were not there. But the moment the number of operations becomes large and number of associated variables becomes large, then we have to make major choices with respect to the register allocation, with respect to the function unit binding. But to begin with the scheduling, you have resource constraints that need to be respected, but otherwise you have a large number of operations and they have to be mapped onto clock cycles. It is not as though you have only one choice, you have a very large number of choices to exercise with respect to scheduling. Actually, all 3 problems would fall into what are called NP-hard problems when you analyze their computational complexity. Scheduling, of course, is a classical problem that is valid in many different contexts. Instances of the scheduling problem arise in a large number of different applications. This is just one such application. But the others, function unit binding, register allocation and so on, they too are difficult problems to solve in general. What do we mean by difficult problem? It is not as though you cannot come up with an algorithm to solve the problem, but you cannot guarantee optimality in the algorithms that you come up with. On one hand, these are practical problems and therefore, we need algorithms that are practical, which means that they should run reasonably fast on large size designs. But what we are compromising is that you are giving up on the claim of optimality. Right? You can't say you have the best possible solution.
Are these polynomial class or exponential class?
Are these polynomial class or exponential class of algorithms? We did not get to the algorithms. Of course, in the subsequent discussion we will talk about specific algorithms for scheduling and register allocation and binding and so on. So, that is the time to discuss the complexity of the respective algorithms, but we are warning ahead of time that you can't expect optimality from practical scheduling problems. Yeah. So, you want them to be polynomial in their complexity, because that is more manageable in a practical tool, but you do give up on the claims of an exact solution. We were here where we generated an FSM. It is not as though there is only one possible FSM. Here it seems as though the problem was simple enough and we scheduled everything into 3 clock cycles, and therefore, this is an FSM with 3 states. But in general, the number of states of the FSM and the structure of the FSM also, these are all variable. These are the result of the scheduling decisions that have been made, but there are a very large number of decisions to be made in the scheduling as also in the other steps of the high level synthesis. That is just to motivate the overall picture of a design space that exists for problems like these. What we have indicated here is a 2-dimensional picture in which you have area on one axis and delay on the other axis, considering that these are the parameters of importance when it comes to evaluating our design. What do each of these points represent? They represent a sample solution. The solution consists of all our decisions of scheduling, resource allocation, binding and so on. It would result in some delay, some area. Delay here just refers to the number of clock cycles, area is the total area of the resulting circuit. So, a large number of possibilities might be there, each of these is a possibility, and I can plot all of them in an area delay curve to understand where all the solutions stand, particularly with respect to each other. Looking at a distribution like this, what can we say about the desirable solutions? So, each is a solution. I have a large number of solutions. Can I throw out some of those solutions right away just by looking at this distribution? I can throw it out if I can establish that there is at least one other solution that is always better than this one with respect to every parameter. What are examples?
The circled one.
The one that I have circled, I can throw that out. Why?
Because there is a solution where which is labeled as Z, that is more efficient in delay as well as area.
Yes. So, I have at least one other point. If I compare these 2 points, it is clear that this is always better than that one. So, I can throw out. So, in fact, I can throw out all of these points that are colored brown. Why can I throw them out? Because there is at least some point in this space that seems to be better than or equal to all those other solutions in the interior of that feasible region. So, this region here we can call infeasible because there are not any points in there. You do need a minimum area and a minimum latency without which a realistic solution might not be there. But there may be a number of solutions in the other space, in the feasible space, all of which are not necessarily interesting. The ones that are interesting we can cover in what is called a Pareto curve. It consists of design points that belong to this class where you do not have another solution that is clearly better than that solution with respect to every axis. But the relationship between these points in the set is that you take any pair of points, compare these 2 points y and x, y is better than x with respect to delay, but x is better than y with respect to area. So, we can capture all of these in what is called a Pareto curve, and all of those solutions would be called Pareto optimal solutions. This is an example of a problem domain where there is not a single best solution. Sometimes your problems might be of the form that there would be a single best solution and the objective would be to find it, but that might not be the case always.
So all of these points have been generated after running the
How did these points get generated? Of course, this is an illustration with respect to comparing a large number of solutions. That does not mean that you must generate all those solutions first and then pick up all the solutions that lie along the Pareto curve. This is just a warning that the design space is large and also an indication that some of those solutions are interesting for us. Automatically it is hard to, at least given that your parameters are just delay and area, it is hard to say that one is better than the other. So, we collect all of them and we could submit these as candidate solutions to a designer who may make a manual decision with respect to which one is best. It could be that the final decision is based on other parameters, not necessarily just delay and area, maybe there are other parameters that come into the picture which might help in pruning the design space down further. Maybe all of these are not interesting with respect to a third parameter called power or security or whatever, there may be a large number of other such parameters. So, maybe we can boil the solution space down to just 3 of them, and then one can take a decision based on the relative importance perhaps of area and delay between the selected designs maybe.
So if I have multiple parameters to look into, let's say delay, area and power, so that would mean that my data is then into multiple dimensions. Then probably doing this kind of analysis manually would be cumbersome.
This is not a manual analysis. This like I said, it is not as though our algorithms are going to generate all of those design points and we are going to select among them. The algorithms are of the kind that will usually generate one of these solutions. The more practical algorithms that we will be using will generate one of them, but perhaps they will generate this one. right. But of course, we want to understand that there are other solutions that are also Pareto optimal, that our algorithm might not be generating at all. That depends on how we have written our algorithm. We do want it to converge fast, we do want it to generate us a valid result first. In the rest of the space, the points that are distributed, they are implicitly being thrown out by whatever our algorithms are for these things. It isn't as though they are being explicitly enumerated and a choice is being made. Yeah.
To put a number of area or delay or maybe other metrics also for a point, the way so far I can understand is the HLS would actually create the design, then compute the delay. So, or is there an early estimation kind of method in place where it doesn't do all the synthesis, unpractical implementation, but it guesses that some of these data points in the design space will have, basically to come up with the Pareto curve, can you do much faster?
HLS tool will always prune the design space and will select a subset out of the large number of design points that are there. There is no hope of enumerating all the possible solutions. The space is just too vast. Even though I have shown a small number of points in this graph here, there is no question of enumerating everything. It just blows up. So, a large number of those points are getting thrown out by HLS. So, if there are some solutions that it is generating for us to investigate further, maybe take it down to physical design or something like that, it has already implicitly done a lot of pruning. That we can easily see as we understand scheduling. When you pick up one of those algorithms like scheduling, there are a very large number of choices that a scheduler needs to make. And in the interest of simplicity of the algorithm, it has to throw out a number of those choices. Who knows? And among them, it could be that the optimal choice actually got thrown out. Yeah, it's certainly possible. Right.
And even in the whole design flow, typically at higher abstraction levels, the much of let's say part performance kind of optimization would have been done at virtual prototyping.
This happens at every stage of the design space. That is the way to keep it manageable and the way to ensure that you don't submit every possible solution all the way to place and route and detect at that time that this design is better than the other. As you know, we are arguing here at a little high level of abstraction when we say this area is greater than that area. We are just adding up all the component areas and we are saying that this is the area of the design. But that is not all, like we had seen earlier. When you actually do the placement and routing, there is the routing related area that we are not taking into account when we just add up the component areas. But such simplifications have to be made in the interest of a practical design scenario. Right? You can't afford to go down the entire path and generate masks for all the possibilities that are there. So, every tool is implicitly making all of those choices and possibly at the end of its step, it is submitting for further investigation a small subset of the possibilities. Let us look at a high level behavioral synthesis flow and put in perspective where the algorithms that we will be discussing fits there. So, you have an input processing stage where however you have specified the input in the form of some kind of SDL, whether it is BSDL or system C and so on, the file input is converted into some kind of an internal representation early on. There are some high level transformations that you would be performing. We will study them immediately afterwards. These are somewhat independent of the target architectures, the details of the algorithms that you would be running in the behavioral synthesis. So, they are sort of abstract and there is a lot in common with what compilers do for instance, because the direction is similar. Okay, then these are the core behavioral synthesis algorithms. They consist of those tasks that we already saw, the scheduling and resource binding and register allocation. After all these decisions are taken, there would be maybe a conversion into an RTL format or some kind of a netlist format, depending on whether it is a reasonably symbolic output like it would be if it is an FSM, or whether it is a more structural output. Of course, either way you can write an HDL out, but you could also write an internal representation in the form of some kind of database which as the final output. Expanding on that first step, which is the input processing, we have an HDL input. The opening step is what is called a lexical analysis. In the lexical analysis, you separate out your VHDL model into tokens, some of which are recognized as keywords. If you have entity is a token, and architecture, the word is a token, and others would be classified as identifiers that are not necessarily keywords, and you would also have separators, you would have constant integers, and so on. So, it is just a classification of the input into a bunch of lexical objects called tokens. These tokens are submitted to a parsing stage where what you have submitted, what you have written in the HDL is verified against a grammar of the language. So, every language has an implicit grammar defined, and the parser first establishes that what you have written is grammatically correct. If not, then you get what is called a syntax error, that is flagged at this stage. You have violated the grammar of the language. If everything is fine, then if there are a few other simple things that we can do at this stage. The semantic checks include things like type mismatches. Okay. These may not directly violate the rules of the grammar, but a separate step usually would be performed after grammar is verified to check whether you have any other errors of the kind of type mismatch. Okay. So, if things are fine, then we store the entire input description in some kind of an intermediate representation, so that we can continue with the rest of the processing. So, it is important to note that you do not get back to the input file. So, in a later stage you do not go back to the VHDL file to see what was the port, what was the architecture, what were the processes, and so on. All of those are somehow captured into an intermediate representation, which of course should be powerful enough to store within itself anything that you could possibly write that is valid in the language.
So what is this parse tree and token? What is a token?
The token is what we are separating the input into. So, if you have entity A is port and so on, each of these is a token, entity is a token, these are words, right, but that is the early stage, that is the first stage of a parser. Right. So, this is a token, that is a token, that is a token, this is a token, if you have semicolon, that is a token. We are just separating out an input stream into different tokens, each is a token. That is language defined. So, the language says what is the separator that is permitted here, right. Typical separators may be space or a tab or a new line and so on, that the language defines what that is. The lexical analyzer's job it is to start with this, to construct these tokens and throw out all of those. So, for example, whether you have 2 spaces here or 3 spaces here or some tabs and so on, all of that is filtered out, because as part of the specification to the lexical analyzer you have said that the space is a separator. So, at that stage all of those artifacts are thrown out.
The next step, what is this tree? This is
the parse tree is what is the output of a parser, where so it is at this stage, in fact your entire design is stored in that parse tree format. Where the tree structure comes from, it is just that that is an output that you construct as you do the parsing. Is no, there is no debate. There is no analysis at this stage. This is purely a syntactical capture, right? The program has been written in some way. This is, by the way, this is identical to what happens in a compiler when you write a programming language. So, of course, as of now, there is nothing that is hardware specific or dependent here. These keywords. So, there is of course a distinction here between a keyword entity. This is expected. So, that is provided as an input to the lexical analyzer. Entity is port, these are the keywords that are already provided. So, that it reads these things a character at a time and it builds that word called entity. How did it build that word? It took these things a character at a time, it looked at that separator and built that word entity, and it is matching it against a set of keywords that we have already submitted to the lexical analyzer, and the output from that part of the lexical analysis is this token number 5 that might correspond to entity. Right. So, that is all that is happening here. So, that is what is output here. It is essentially a stream of tokens. This entity is a known token, is not a known token. So, it may say that this is an identifier. It is just some identifier, not one of the keywords, and it also will pass what that string is, so that somebody later on can do something about it. That is all that is there. When it sees a semicolon, it says that this is a semicolon. I am already informed that a semicolon is one of the recognized characters of the language. So, that is also a token. So, that is all that is here. I have a stream of tokens as the output of the lexical analysis. Now, that parsing stage consists of a verification of the grammar. So, just like we gave some rules to the lexical analyzer, those rules were these are the keywords, these are some of the characters that I am expecting in this language, they mean something to me. So, so far it is not checking whether that character should be there or not at that particular place. That is the job of the grammar verification strategy. Here it is just saying that I found that character, right. So, that character means something, that is part of this stream of tokens that I am sending. But it is intelligent enough, of course, to realize that you have a P here, that P does not match any keyword, but it will extend the match, it will try to extend that word until a match could be found. So, it will read the next one. You see that the word terminates when that separator that we have already specified, we have specified what the separators are. When that is encountered, that is when that word is constructed and is first matched against the set of keywords that you have specified. There is a little finite state machine that is built as part of that lexical analyzer. We are not going into that, but you can see conceptually it is just a stream of output tokens from here. Meaning is not necessarily analyzed at this stage, but the next stage is a grammar verification. So, to this we somehow have to indicate the entire grammar that is expected for the language. What so, for our entity specification, what would that grammar be? It would be, let us say I have an entity, that is a token. So, the stream of tokens that are acceptable for a particular statement. This is an entity statement, there are many kinds of statements here. So, let us say it is an entity declaration, and what would the entity declaration look like in the most general case? You already know the syntax, you know examples of how to write entities. How would you describe it formally? You start with the keyword entity, then there is an identifier. That identifier is something that the user is choosing, right. It does not matter anything, as long as it does not conflict with one of our keywords, we will accept it, or some rules might be there on what you will permit and what you will not permit in an identifier. So, that could be there. So, I say entity and then identifier, then is should be there, then port. Okay. Remember, I can have port, and this is a token, this is also a token, parenthesis is also a token. After that what? I have some things that is a little more complex, right. I have to somehow carefully define what is there, because that is not fixed. You may have any number of ports, and my grammar rules should be such that it is able to anticipate and correctly match and capture a list of ports that is of variable length. So, we will get to that, but after that list is captured, I would have a closing parenthesis and I may have a semicolon. Let me just call it a port list. So, I will call this as an identifier. I will say that this should be followed by a port list. Let me just call this that list of ports that could be of variable length. Remember, even though I have formatted it like this, your own format and indentation, all of that is different. So, that is handled in a way that we inform the lexical analyzer that the separator character is space or tab or new line and so on. So, this is not sacrosanct that I wrote it in the next line, that is immaterial here, because we are just taking tokens here. That you put 3 more lines in between is something that is lost at the interface of the lexical analyzer and the parser. The parser does not even see that you have put tabs or new lines or 10 lines or 20 lines, 20 blank lines. Right. That is a port list. And then the generic parameters might have to be given. So, there would be an associated generic list. Then I would have that end ID, and if there was a semicolon, you can say that if there was a semicolon is also one of our tokens. So, you can say there is a semicolon here, you can say the semicolon here. You see that this is an effective high level capture of what to expect in entity declaration. Any entity that the language permits you to write, I should be able to anticipate in what is called a grammar rule. This is one grammar rule of the language. It is worth going into a little more detail. This is of course not the complete description. What is port list, what is the generic list, these two we have not defined. So, but this is the rule for an entity. Okay. This is one rule of the language. Let us say we start off with an overall rule. What does a complete VSDL model consist of? What we just said is just the entity part of it, but your entire design consists of what? In addition to the entity, there is an architecture. So, I say that there is a model, a complete model may consist of an entity followed by architecture, but actually I may have any number of architectures. Remember that you may have multiple architectures. So, you can maybe have a list of architectures. That is my single line grammar rule for the highest level structure of the language. Of course, we are developing this a little informally. The language will have a reference manual where a precise grammatical structure is outlined. It is worth taking a look at it if sometimes we are not clear about whether the syntax should be this way or that way. Those rules are what are sacrosanct for a language. Every language comes with such a bunch of grammar rules that have to be clearly satisfied. Okay, so I had model consisting of entity and arc list. Entity is what we just developed. So, that is my entity. So, similarly architecture, I would have another rule. Within that architecture, I would allow a number of concurrent processes or signal assignments. Each now getting to a signal assignment, you can see how this is recursively developed, right. I can say that a signal assignment should consist of in the very simple case, I have a signal or an identifier, as of now it is just an identifier. You have less than or equal to, this is also a token. I should have alerted the lexical analyzer to expect such a thing that looks like less than or equal to, but depending on where it is used, it should be able to correctly disambiguate the meaning of that symbol. Okay. Then I will have an expression, let me just call it an expression, right. This is the equivalent of A is equal to B plus C. That is an architecture statement, a concurrent signal assignment at the architecture level, and that is anticipated by this kind of a rule that is specified to the parser. Okay, that is part of our grammar. So, I have signal, this assignment operator, an expression. That expression I should be able to capture any kind of expression. You may have hundreds of operations in there, and that is also a valid expression, right. There is no limit to how complex that expression is. There is one more thing, this also needs to be specified. This grammar has to have everything, so that semicolon token also goes there. That is simplified version of a concurrent signal assignment for us. Okay. And so, that is one. In the architecture, as part of the architecture's grammar, I should be able to say that I can have any number of such constructs, each of which is either a concurrent signal assignment or a process, right, because we said that they are all allowed at the architecture level, and they are all operating independently with respect to one another. Then what? So, this is simpler, but the expression in turn I should have another rule that says expression means what, right. What might that translate to? Each needs a rule. So, for expression I need a grammar rule. What might that be? Ending in semicolon. Actually, that is not true. The statement ends in a semicolon. Expression is this part of it only, right. So, expression does not end in semicolon. In this particular language, other languages it might be different. What might a rule be for an expression? Yes, it would be some sequence of operands and operators. Operands are what here? They are those identifiers, right. So, an example would be I have an identifier, I have an operator and another identifier perhaps. That is an example. You actually have to allow for many different kinds of operator. This is a binary operator that we just said, but that is okay. I should be able to expand that expression rule to all the kinds of operators that you may have. So, if you have something like not A equals not B, that does not fit this format. So, you need a different, so that maybe has this operator. Actually, in the general case it is an expression, right, an operator followed by another expression. So, it is recursively specified in that way, and then among the rules of the expression would be that you just have an ID, that is also an expression. That could be used to hierarchically compose complex expressions, because let us say I specified two things. I have expression could be expanded as just a simple ID, or I say it could be expression operator expression. Okay. Using that, just these two rules, let us see if we can reconstruct an expression like this: A plus B plus C plus D, or maybe let me make it minus. So, this part of it is not defined yet. I need a separate rule for me to tell me what is allowed as part of that operator. So, I add another rule that says operator could be plus, it could also be minus. Both are binary operators. Where did that plus and minus come from? We have to instruct the lexical analyzer to return that token. It is just a token, that if you see plus that character, then you should return that plus token. If you see the minus character, you should return the minus token. These are just tokens. Fine. Identifier of course is another token. So, can we construct this complex expression from multiple applications of the expression rule. You see that at an elementary level A, B, C, D, these are what? These are recognized as identifiers by the lexical analyzer itself. So, that is an identifier, that is an identifier, that is an identifier. The plus is an operator. These, so that rule that I have here for the operator, that would be matched for me to get an operator from that plus character, right. So, I have an operator, that is what it looks like. Okay. Then let us proceed left to right, and finally, we want to recognize that this whole thing is an expression, right. So, that is the job of a parser. You see that this part means, so expression being the simple identifier means that all of these guys, right, all of these identifiers can be so let us say recognized as expressions by themselves, right. So, this could be recognized as an expression, this and this is recognized as an expression. Okay. Now, that rule for the binary operator could be matched, because you say that an expression could be composed of an expression, an op and an expression. I have, so I have, fine, this is a recognition of an expression. So far we are proceeding just left to right. After that I have this, I have that operator and I have this expression. These could be matched to generate a new expression. And finally, this and this could be matched to finite expression. And in the process what I have done is there was a complex specification of an expression. You can see how this generalizes to any number of operators and any level of complexity of a single expression. So, essentially we have recognized that whole thing as an expression. The tree structure comes about from this recognition process. So, this whole thing is what would be called a parse tree. The grammar itself has a tree structure in the way it is specified, and the way it is recognized, a tree is explicitly built out of this recognition process. So, we did that informally here, but this is formally what happens in a parser, that you have a large number of these kinds of rules that are specified that constitutes the grammar of a language, and you have specified the model in a file with some syntax. This kind of a process can be used first of all to check whether your syntax is correct or not. If it is incorrect, then some rule will fail in its matching. It started the matching process, but let us say you did not put a recognized operator, you put some garbage symbol out there. This recognition process that we just informally went through now, that will notice the violation and will report what is called a syntax error, that you provided something and I was not expecting that token at that time. So, those are the syntax checks that are first done. Yeah.
In this representation,
Yeah.
in the flow chart, it seems that lexical analyzer will not build the final IR data structure to start with, or will not do anything about it,
Right.
but will just create the tree and pass the entire thing to the parser.
Yeah, but just to correct, the lexical analyzer is not building it. Lexical analyzer is only sending a stream of tokens to the parser. It is the parser, they are not concurrent, they are sequential. The output of a you could implement it in concurrently, but the output is just a bunch of numbers and strings from the lexical analyzer. It is at the parser level that we are first going through this recognition process, but you can see that as part of that recognition process I can build that data structure.
Yes, that's what I was trying to.
Right. That parse tree is my data structure that is being built. Of course, if there is an error, then everything is abandoned. It does not make sense to build the parse tree if your program is wrong, right. But at the end of it, if everything is recognized and a correct model is recognized, this you can see this has nothing to do with VSDL. It is just that this same process would be followed irrespective of what your language is. The rules would be different for different languages. Right. But at the end of it, if the parsing is successful, then you have constructed along the way elements of that parse tree, and then so there is no separate parse that is needed for actually creating the representation. You do have a valid representation. That is what we are calling this intermediate representation at this stage.
So in hierarchical representations, this was flat. Flat in the sense we didn't have entity inside entity called inside entity. So let's say we have a
You did not have an instantiation
yes.
of an object, yes.
So in case we have a hierarchical sense in the input data,
Yeah.
then would it make sense to create IR as soon as we are done with one of the hierarchy there?
Okay, in general, there is an interesting question of should you put more and more intelligence into that parsing process. As of now, we are saying that the job of the parsing process is just this recognition part. At the end, it creates some data structure for us, and in a later stage, we will analyze that data structure. Semantic checks is that. To find a type mismatch, what is the right time? According to this diagram, it is you are completely doing the recognition process, building the parse tree, and then moving to the type mismatch which might have been there in the first line itself. So your question is why don't I just do that immediately, and that would save me some useless work, because I could have come back and said this is your type. Yeah, it's an interesting question. It isn't as simple as this. So some elementary checks are performed along the way. This is just a conceptual picture, but simple checks that are essentially of a local level, those are okay to perform as you are building it. Remember, there is a trade-off involved. This is one side of the argument. The other side is, as you put more and more intelligence into the parsing process, you are delaying the parsing. There is a large file to be processed and an error is there in the late stages, then you are unnecessarily doing a lot of useless work, which leads to an engineering solution of the kind that you do very simple checks during the parsing, but you do not do complex checks. So it's possible that at the end of the parsing there would still be some kind of errors that are not locally detectable. You have to do a lot of traversal to find that there is a mistake of some way. But simple type errors you could also detect during this phase.
Yeah. Pipeline pipeline. One is working, then next will follow.
These things could be arranged as independent processes that are working as soon as, but yeah, there is a level of, there is some argument for simplicity of the design also. You do want to reserve most of the time for later analysis and optimization. This step you might not want to spend too much time on. Right. Yeah.
So is there any kind of optimization in the front end? So for example, let's say there is some dead code or description or something.
Optimizations are almost never performed at this stage, not because they do not make sense, but it is just that you may have to throw out everything just because there is a syntax error much later. So right, it might be worth it, but then if everything is okay, then maybe perhaps you might save some time also in the process. But just in the interest of simplicity, they do not do too much of optimization. There are some things that are done to optimize this step, the lexical analysis and the parsing step. What happens is when you have a syntax error, you could abort the whole process immediately, but you can try to patch up that process, or somehow your entity specification or declaration did not match. So there was a syntax error in the entity declaration itself. You could abandon everything and just say that this is an error, but it is often considered useful from a user's point of view to give you all the errors that are there in your program, not one at a time. You may, if you have 200 errors, you want to fix all of them together. It is irritating to run the compiler again and again to be informed that there is a semicolon that is missing, and then you go back and say this comma is missing, and so on. So, from a user's point of view, it is a nice thing to say I want all my errors to be reported at once, but you see that actually imposes some, it creates some very serious technical challenges. How do you go forward? We talked about, while this was not a formal exposition on how parsing is done, you got the sense of how it is done, right? The rules are there, we try to match the rules, and depending on what you have specified, we pick the appropriate rule. This is a simplification, but how do you decide the appropriate rule is an interesting question. But either way, you see that you run into technical difficulties when the rule is not matching. Then what happens? How do you progress? The user wants all the errors to be determined when in fact we have got completely off track because the entity rule itself did not match. Right. So they do a lot of smart things to recover from errors that are specified by imperfect users like us. Often one can recover in a reasonable way, like a semicolon is missing. You can patch it up, assume that the semicolon was there and just go ahead. Even though the statement rule did not match, you assume that it matched and then anyway proceed to the next statement and so on. That explains sometimes when you compile a program, you get all kinds of errors that you have no clue about. Your reaction is, I do not have all of these things in my program, why is it reporting? But what happened is that it got confused because an appropriate patching up could not be performed, and it went into some other rule where it was expecting something else, and you are saying, where are all those things in my program? They are not there. So, it is useful most of the time, but sometimes might throw you off. In a C++ compiler, sometimes you might have seen examples of all kinds of errors that you do not know where it came from, but that happens because of two things. One is this, other is because you are using libraries from somewhere and it says that this operator is not overloaded for that object, right. Yeah.
So, input for this flow is any standard SDL language. So, is there any standard for this intermediate representation as well? Or?
Oh yes, but that is the topic of further discussion. Yes, we do want that intermediate representation to be language independent, because languages may change, but those changes may be of a very superficial nature, because it is just like instead of entity you have module or something like that, but your synthesis mechanisms are not going to be changed just because the language changes. So, usually you would design that intermediate representation in a way that you are shielded from changes in the language. You can't be shielded 100%, because of course, you know that if you add a new keyword to the language, then of course the parser has to change. That keyword has to be accommodated, hopefully with a very minor change. The representation also has to change, but hopefully the changes will be minor. The design is such that it is intended to be generic and would stay through iterations of language or variations of language, newer and newer versions of the language and so on. We try to make it independent as far as possible, just so that our analysis and later steps are not influenced by change of language or changes of that nature.
Syntax error I understand, but what kind of a check is semantic checks?
Type mismatch is a semantic check. You say A equal to B, right? If you have a statement that says A equal to B plus C and so on, right. This is of some type and all of these guys are of different types. You know, the type of that expression may not be obvious to start with. This, we know the type of A, we know the type of B, C and so on. At the end of this, so some analysis would be needed to find what is the type of that entire expression, because you may promote some types. One is an integer and the other is a floating point number. The rules of the grammar have to explicitly permit this, which they do, but it would also be that at the end of this you add an integer to a float, what kind of expression do you get? What is the type of the resulting expression? That this results in a float is a language specification. We do not make that assumption, it is specified in a way that is reasonable, but you have to actually do all of this to find out what the type is for an expression, and the A equals something. So, this might actually, from the point of view of matching the grammar rule, this statement might be okay, right, but from a type point of view there might still be a mismatch. That is an example of a semantic check. There is more to the language than just the grammar rule. So, those other things need to be verified also. So, a number of other things would also fall in this category, for example, redeclaration of a variable, right. So, you have an int a, at some other stage you also have an int a, right. Both of these are valid statements by themselves, but the second declaration is in error because you had already declared that variable first. That is not obvious from the rules of the grammar, because the grammar will correctly recognize both this statement and these statements. There is no harm in the statements itself, but they are linked in a way that there is an error that is created because of this. So, those kind of errors would fall in the semantic chain. They are not necessarily performed sequentially, like we are saying. This kind of an error is easily detectable at the time that you get to the second statement, get to this declaration. You should be able to detect that in the current scope there is an A that is already visible, it has already been declared. So, you could, if you want, do this kind of semantic check during the parsing itself. Okay. So, it is important that the design representation be almost language independent to the extent possible. There will be some features that are there in one language that are not there in the other language, and so for those you do need the intermediate representation to be able to capture also. But it is okay to have that representation that you are using being somewhat of a superset of a particular language. Right. If in a particular language a feature is not there, then it is all right, you do not create elements of that nature when you create your representation. What else? So, it should be easy to add a new front end for a new language. Normally these analysis techniques, synthesis techniques and so on, they might last longer than a particular language. New languages may evolve. We do not redesign everything from scratch, tools from scratch when languages evolve, because most of things that we are doing might still be the same. So, it should be of the kind that ideally I should have only a new front end when the language changes, which means that the parser and all of that, those things would change, but the synthesis steps hopefully would not need to change. Those are elementary requirements. Then what is expected within that IR itself? It should be relatively easy to do transformations. Why transformations are important, we will get to as soon as we talk about optimizations. We perform as part of the synthesis process all kinds of transformations on the code. Transformations means you read it in the form of a tree structure at the end of the parsing, but we do not keep it in that way. Depending on what is it that we are doing, we modify that representation in various ways. Either way, I should have easy ways to traverse the design. I should have insertion, deletion, replacement, those kind of features. These are tree or graph kind of structures anyway. So, I should be able to traverse a tree or a graph. I should be able to replace some section of a graph with a new section that I have created that would represent an optimization or a transformation. The right representation would be different in different parts of that overall flow. So, early on it would be what is called an abstract syntax tree, that is the tree the parser creates, but that structure may or may not be best in later stages of the design. Of course, we will be talking about these representations in more detail, but the idea of a controlled data flow graph or some variation of this is something that is often used through large parts of the synthesis process. Let us just try to understand what that controlled data flow graph looks like, because in various algorithms later on we may be using implicitly this CDFG, that the what we have written in the HDL is captured in the form of a CDFG, so that other algorithms operate on the CDFG. They do not operate on the file that you have written, they operate on this intermediate representation. Okay. So, this is a combination of two things. One is a control flow graph that is responsible for capturing sequencing, conditional branching and looping structures wherever control flow exists in our specification. Data flow graph is somewhat of an orthogonal structure. It captures computation essentially. These are easier to illustrate with an example. Let us say this is what my HDL was looking like, and I did not respect a particular HDL here. This looks more like C, but it does not matter. Remember, this representation is supposed to be independent of the language. So, we can use various HDLs at the input. Let us say I have a conditional structure here, and that is getting captured in the form of a control construct that looks like this. This refers to a forking structures where I have two different branches. This corresponds to the then part, and this corresponds to the else part. That is just a dummy node as of now. It does not carry that information of what is happening in that branch. It is just carrying the information that there is a branch there, right. And this idea is called a basic block. It's terminology from a compiler. You can think of it just as a sequence of statements with no branching within it. It is more formally defined separately, but it is like within a branch you have a sequence of statements. There is only one flow of control within a basic block. Other elements that go into the definition of a basic block is that there should be only one entry into that basic block and one exit from the basic block. How is that different from just a sequence of statements? A language may permit you to go to a particular statement from somewhere else. When that happens, you see that this definition is violated. If this is my sequence of statements constituting a basic block, then I have multiple entries. This is one entry, that is the default entry, the first statement, but if you allow entry from somewhere else to the middle of that sequence of statements, then that is no longer a basic block. Why that is defined that way is that we want to be able to move a basic block maybe from one place to the other or something like that, and some properties are not retained if you allow jump from some part of the code to some other part. So, anyway, that is what the basic block is. For now, it is the longest sequence of statements that has only one entry and one exit. So, this is one such basic block, that is one such basic block, and so on. Okay. That is not captured in the CFG. The CFG is only capturing in a dummy node like this that there is a basic block. So, we have not yet completely captured in an intermediate representation that SDL, but at least the control part of it we have captured. Generalizing into a multi-way branch, if you have a case statement with multiple entries, then that is what that generalization is. So, there is a fork, but you have multiple branches in that way. All of these come together in a corresponding join node before we proceed with other elements of the control flow graph. This is just a sample. You can think of other constructs. If you have a loop, then what that might translate to, and so on. These can be composed with each other in a natural way. So, first of all, there can be hierarchy in the conditional structures that we write. That could be translated to a hierarchical control flow graph in this way. So, the inner if statements corresponds to that part of the structure. These are all graphs, even though I have shown these using different colors and different forms and so on. They are all nodes in the graph, and they would be distinguished from each other through properties of the node, that properties that we annotate onto the node. So, that is the hierarchical structure. There can be sequences of these structures. So, this is a basic block by itself, that is this part, this corresponds to that part, and that switch that comes next corresponds to this part. And these are dependencies, the sequentiality is maintained through the presence of edges like that. So far we haven't said anything about what we do with it. This is only a representation. As of now, this is what the user has written, and we just have some intermediate graph based structure for capturing the specification. We are not doing any optimization, but as part of an optimization, it is possible we restructure this graph in some way. Right. Completing this, I can have a data flow graph. I had the statement that as of now we just had a dummy node, but the computation part of it we can capture in what is called a data flow graph. So, I have nodes corresponding to these operators. There may be other nodes corresponding to these operands depending on where they came from. This is just the most general form. You might not need all of these nodes to read an A. Remember, in the general case, maybe reading of an A corresponds to a memory operation or something like that. So, that a node might actually need to be created. But I have nodes corresponding to both operands and operators. Output is going into Y, and these edges in the data flow graph represent dependencies between nodes. Right. If I have a sequence of statements like this part of it is the first statement. Right. I have z equals y plus 1, that is the second statement, but there is an edge from the first output to the second input. So, that operator's output is an input to the second operator. The dependency is represented by introducing an edge between the two nodes. The entire basic block need not be a one connected data flow graph. There may be other parts that are unconnected, but the whole thing together is a data flow graph. So, it corresponds to one sequence of statements that you have. So, a basic block in a code would translate to a data flow graph. And with that I can compose a control data flow graph out of it, where the high level structure, the control structure is captured in the form of a control flow graph. But what is missing from here is the computation part of it. What happens in each basic block, that is not captured. So, this basic block translates to a DFG, that other basic block here translates to some other DFG, and in fact, the way we have written this, the fork also has a computation associated with it. So, there is a different DFG. This is just by way of illustration. You might actually move that computation out into the prior code. So, that might actually become part of the previous basic block, and that is where that DFG might be absorbed. But a control data flow graph is an overall structure where you have a hierarchy of graph structures. The higher level is a control flow graph where you have captured control flow, and the basic blocks within that, the computation that is captured in the basic blocks is expanded out in the form of individual data flow graphs. Yeah. Let us stop here for today.
Data is annotated as weights here in the control data flow graph.
So, yes, we just had the pictures here, we did not label the edges, but there would be a label. So, over here I would put that label here on the edge. Yeah. Sometimes those labels are, like we discussed the other day, are explicitly declared variables, sometimes they are implicitly created by us inside the synthesis tool, but they still have a name and we annotate those names wherever we have information about the name.